Muḥammad ibn Mūsā al-Khwarizmi, Arabized as al-Khwarizmi and formerly Latinized as Algorithmic, was a Persian polymath who produced vastly influential works in mathematics, astronomy, and geography. Around 820 CE he was appointed as the astronomer and head of the library of the House of Wisdom in Baghdad. Al-Khwarizmi's popularizing treatise on algebra presented the first systematic solution of linear and quadratic equations. One of his principal achievements in algebra was his demonstration of how to solve quadratic equations by completing the square, for which he provided geometric justifications, because he was the first to treat algebra as an independent discipline and introduced the methods of reduction and balancing, the transposition of subtracted terms to the other side of an equation, that is, the cancellation of like terms on opposite sides of the equation. He has been described as the father or founder of algebra. The term algebra itself comes from the title of his book, the word al-jabr meaning completion, or rejoining. His name gave rise to the terms algorism and algorithm, as well as Spanish and Portuguese terms algoritmo, and Spanish guarismo, and Portuguese algarismo meaning digit. In the 12th century, Latin translations of his textbook on arithmetic, Algoritmo de numero indorum, codified the various Indian numerals and introduced the decimal positional number system to the Western world. The compendious book on calculation by completion and balancing, translated into Latin by Robert of Chester in 1145, was used until the 16th century as the principal mathematical textbook of European universities. In addition to his best-known works, he revised Ptolemy's geography, listing the longitudes and latitudes of various cities and localities. He further produced a set of astronomical tables and wrote about calendaric works, as well as the astrolabe and the sundial. He also made important contributions to trigonometry, producing accurate sine and cosine tables, and the first T. Now we will talk about his biography. Few details of al-Khwarizmi's life are known with certainty. He was born into a Persian family, and Ibn al-Nadim gives his birthplace as Khwarizm in Central Asia. Muhammad ibn Jarir al-Tabari gives his name as Muhammad ibn Mūsā al-Khwarizmi al-Majusi al-Kutrabali. The epithet al-Kutrabali could indicate he might instead have come from Kutrabal, a viticulture district near Baghdad. However, Rashed denies this. There is no need to be an expert on the period or a philologist to see that al-Tabari's second citation should read, Muhammad ibn Mūsā al-Khwarizmi and al-Majusi al-Kutrabali, and that there are two people between whom the letter wa has been omitted in an early copy. This would not be worth mentioning if a series of errors concerning the personality of al-Khwarizmi, occasionally even the origins of his knowledge, had not been made. Recently, G.J. Toomer, with naive confidence, constructed an entire fantasy on the error which cannot be denied the merit of amusing the reader. Regarding al-Khwarizmi's religion, Toomer writes, another epithet was given to him by al-Tabari, al-Majusi, would seem to indicate that he was an adherent of the old Zoroastrian religion. This would still have been possible at that time for a man of Iranian origin, but the pious preface to al-Khwarizmi's algebra shows that he was an Orthodox Muslim, so al-Tabari's epithet could mean no more than that his forebears, and perhaps he in his youth, had been Zoroastrians. Ibn al-Nadim's Kitab al-Firist includes a short biography on al-Khwarizmi together with a list of his books. Al-Khwarizmi accomplished most of his work between 813 and 833. After the Muslim conquest of Persia, Baghdad had become the center of scientific studies and trade, and many merchants and scientists from as far as China and India traveled there. As did al-Khwarizmi, he worked in the House of Wisdom established by the Abbasid Caliph al-Ma'mun, where he studied the sciences and mathematics, including the transliterature. Now we will talk about his contributions. Al-Khwarizmi's contributions to mathematics, geography, astronomy, and cartography established the basis for innovation in algebra and trigonometry. His systematic approach to solving linear and quadratic equations led to algebra, a word derived from the title of his book on the subject, the compendious book on calculation by completion and balancing. On the calculation with Hindu numerals, written about 820, was principally responsible for spreading the Hindu-Arabic numeral system throughout the Middle East and Europe. It was translated into Latin as Algorithmi de numero indorum. Al-Khwarizmi, rendered as Latin algoritmi, led to the term algorithm. Some of his work was based on Persian and Babylonian astronomy, Indian numbers, and Greek mathematics. Al-Khwarizmi systematized and corrected Ptolemy's data for Africa and the Middle East. Another major book was Kitab Surat al-Ard, the image of the earth, translated as Geography, presenting the coordinates of places based on those in the geography of Ptolemy but with improved values for the Mediterranean Sea, Asia, and Africa. He also wrote on mechanical devices like the astrolabe and sundial. He assisted a project to determine the circumference of the earth and in making a world map for al-Ma'mun, the caliph, overseeing 70 geographers. When, in the 12th century, his works spread to Europe through Latin translations, it had a profound impact on the advance of mathematics in Europe. His contributions in Algebra, the compendious book on calculation by completion and balancing, is a mathematical book written at approximately 820 CE. The book was written with the encouragement of Caliph al-Ma'mun as a popular work on calculation and is replete with examples and applications to a wide range of problems in trade, surveying, and legal inheritance. The term algebra is derived from the name of one of the basic operations with equations described in this book. The book was translated in Latin as Liber Algebrae al-Muqabbala by Robert of Chester, hence algebra, and also by Gerard of Cremona. A unique Arabic copy is kept at Oxford and was translated in 1831 by F. Rosen. A Latin translation is kept in Cambridge. It provided an exhaustive account of solving polynomial equations up to the second degree, and discussed the fundamental methods of reduction and balancing, referring to the transposition of terms to the other side of an equation, that is, the cancellation of like terms on opposite sides of the equation. Al-Khwarizmi's method of solving linear and quadratic equations worked by first reducing the equation to one of 6 standard forms, where b and c are positive integers. The above discussion uses modern mathematical notation for the types of problems that the book discusses. However, in al-Khwarizmi's day, most of this notatio. Several authors have also published texts under the name of Kitab al-Jabr wal-Muqabbala, including Abu Hanifa Dinawari, Abu Kamal Shuja ibn Aslam, Abu Muhammad al-Adli, Abu Yusuf al-Misasi, Abd al-Hamid ibn Turk, Sind ibn Ali, Sal ibn Bisar, and Sharaf al-Din al-Tusi. J. J. O'Connor and E. F. Robertson wrote in the MacTutor History of Mathematics Archive, perhaps one of the most significant advances made by Arabic mathematics began at this time with the work of al-Khwarizmi, namely the Beginnings of Algebra. It is important to understand just how significant this new idea was. It was a revolutionary move away from the Greek concept of mathematics, which was essentially geometry. Algebra was a unifying theory that allowed rational numbers, irrational numbers, geometrical magnitudes, etc., to all be treated as algebraic objects. It gave mathematics a whole new development path, so much broader in concept to that which had existed before, and provided a vehicle for future development of the subject. Another important aspect of the introduction of algebraic ideas was that it allowed mathematics to be applied to itself in a way that had not happened before. R. Rasht and Angela Armstrong write, Al-Khwarizmi's text can be seen to be distinct not only from the Babylonian tablets but also from Diophantus Arithmetica. It no longer concerns a series of problems to be solved, but an exposition that starts with primitive terms in which the combinations must give all possible prototypes for equations, which henceforward explicitly constitute the true object of study. On the other hand, the idea of an equation for its own sake appears from the beginning and, one could say, in a generic manner, insofar as it does not simply emerge in the course of solving a problem, but is specifically called on to define an infinite class of problems. According to Swiss-American historian of mathematics, Florian Cajori, al-Khwarizmi's algebra was different from the work of Indian mathematicians, for Indians had no rules like the restoration and reduction. Regarding the dissimilarity and significance of al-Khwarizmi's algebraic work from that of Indian mathematician Brahmagupta, Carl Benjamin Boyer wrote, "It is true that in two respects the work of al-Khwarizmi represented a retrogression from that of Diophantus. First, It is on a far more elementary level than that found in the Diophantine problems, and, second, the algebra of al-Khwarizmi is thoroughly rhetorical, with none of the syncopation found in the Greek Arithmetica or Brahmagupta's work. Even numbers were written out in words rather than symbols. It is quite unlikely that al-Khwarizmi knew of the work of Diophantus, but he must have been familiar with at least the astronomical and computational portions of Brahmagupta, yet neither al-Khwarizmi nor other Arabic scholars made use of syncopation or negative numbers. Nevertheless, the al-jabr comes closer to the elementary algebra of today than the works of either Diophantus or Brahmagupta, because the book is not concerned with difficult problems in indeterminate analysis but with a straightforward and elementary exposition of the solution of equations, especially that of the second degree. The Arabs in general loved a good clear argument from premise to conclusion, as well as systematic organization, respects in which neither Diophantus nor the Hindus excelled. His contributions in arithmetic. Al-Khwarizmi's second most influential work was on the subject of arithmetic, which survived in Latin translations but lost in the original Arabic. His writings include the text Kitab al-Hisab al-Hindi, Book of Indian Computation, and perhaps a more elementary text, Kitab al-Jami, Tafriq al-Hisab al-Hindi, Addition and Subtraction in Indian Arithmetic. These texts described algorithms on decimal numbers, Hindu-Arabic numerals, that could be carried out on a dust board. Called tact in Arabic, Latin, tabula, a board covered with a thin layer of dust or sand was employed for calculations, on which figures could be written with a stylus and easily erased and replaced when necessary. Al-Khwarizmi's algorithms were used for almost 3 centuries until replaced by al-Uqlidasi's algorithms that could be carried out with pen and paper. As part of the 12th century wave of Arabic science flowing into Europe via translations, these texts proved to be revolutionary in Europe. Al-Khwarizmi's Latinized name, algorismus, turned into the name of the method used for computations, and survives in the modern term, algorithm. It gradually replaced the previous abacus-based methods used in Europe. 4 Latin texts providing adaptations of al-Khwarizmi's methods have survived, even though none of them is believed to be a literal translation. Dixit Algorismi, published in 1857 under the title Algoritmi de Numero Indorum. Liber al-Khwarizmi de Practica Arithmetis Liber Asagagarum al-Khwarizmi Liber Pulveris Dixit Algorismi, thus spake al-Khwarizmi, is the starting phase of a manuscript in the University of Cambridge Library, which is generally referred to by its 1857 title Algoritmi de Numero Indorum. It is attributed to the Adelard of Bath, who had also translated the astronomical tables in 1126. It is perhaps the closest to al-Khwarizmi's writings. Al-Khwarizmi's work on arithmetic was responsible for introducing the Arabic numerals, based on the Hindu-Arabic numeral system developed in. His contributions in astronomy. Al-Khwarizmi's Sij al-Sindhind, Arabic, Astronomical Tables of Siddhanta, is a work consisting of approximately 37 chapters on calendrical and astronomical calculations and 116 tables with calendrical, astronomical and astrological data, as well as a table of sign values. This is the first of many Arabic sijas based on the Indian astronomical methods known as the Sindhind. The work contains tables for the movements of the sun, the moon, and the 5 planets known at the time. This work marked the turning point in Islamic astronomy. Hitherto, Muslim astronomers had adopted a primarily research approach to the field, translating works of others and learning already discovered knowledge. The original Arabic version, written c. 820, is lost, but a version by the Spanish astronomer Maslama ibn Ahmad al-Majriti c. 1000 has survived in a Latin translation, presumably by Adelard of Bath, January 26, 1126. The 4 surviving manuscripts of the Latin translation are kept at the Bibliothèque Publique, Chartres, the Bibliothèque Mazarine, Paris, the Biblioteca Nacional, Madrid, and the Bodleian Library, Oxford. His contributions in trigonometry. Al-Khwarizmi's Sij al-Sindhind also contain tables for the trigonometric functions of sines and cosine. A related treatise on spherical trigonometry is also attributed to him. Al-Khwarizmi produced accurate sine and cosine tables, and the first table of tangents. His contributions in geography. Al-Khwarizmi's third major work is his Kitab Surat al-Ard, Arabic, book of the description of the Earth, also known as his Geography, which was finished in 833. It is a major reworking of Ptolemy's 2nd century geography, consisting of a list of 2,402 coordinates of cities and other geographical features following a general introduction. There is only one surviving copy of Kitab Surat al-Ard, which is kept at the Strasbourg University Library. A Latin translation is kept at the Biblioteca Nacional de España in Madrid. The book opens with the list of latitudes and longitudes, in order of weather zones, that is to say in blocks of latitudes and, in each weather zone, by order of longitude. As Paul Gallès points out, this excellent system allows the deduction of many latitudes and longitudes where the only extant document is in such a bad condition as to make it practically illegible. Neither the Arabic copy nor the Latin translation includes the map of the world itself. However, Hubert Dornick was able to reconstruct the missing map from the list of coordinates. Dänicke read the latitudes and longitudes of the coastal points in the manuscript or deduces them from the context where they were not legible. He transferred the points onto graph paper and connected them with straight lines, obtaining an approximation of the coastline as it was on the original map. He then does the same for the rivers and towns. Al-Khwarizmi corrected Ptolemy's gross overestimate for the length of the Mediterranean Sea from the Canary Islands to the eastern shores of the Mediterranean. Ptolemy overestimated it at 63 degrees of longitude, while al-Khwarizmi almost correctly estimated it at nearly 50 degrees of longitude. He also depicted the Atlantic and Indian Oceans as open bodies of water, not landlocked seas as Ptolemy had done. Al-Khwarizmi's prime meridian at the Fortunate Isles was thus around 10 degrees east of the line used by Marinus and Ptolemy, most medieval Muslim gazetteer. His other contributions, Ibn al-Nadim's Kitab al-Fihrist, an index of Arabic books, mentions al-Khwarizmi's Kitab al-Tariq, a book of annals. No direct manuscript survives. However, a copy had reached Nusaybin by the 11th century, where its metropolitan bishop, Mar Elias Bar Shanaya, found it. Elias's chronicle quotes it from the death of the Prophet through to 169r, at which point Elias's text itself hits a lacuna. Several Arabic manuscripts in Berlin, Istanbul, Tashkent, Cairo, and Paris contain further material that surely or with some probability comes from al-Khwarizmi. The Istanbul manuscript contains a paper on sundials. The Fihrist credits al-Khwarizmi with Kitab ar-Rukama. Other papers, such as one on the determination of the direction of Mecca, are on spherical astronomy. Two texts deserve special interest on the morning with Marifat Sarat al-Mashriq fi Kul Balad, and the determination of the azimuth from a height Marifat al-Samt min Qibal al-Irtifa. He also wrote two books on using and constructing astrolabes.